Okay, so I had paused my recording, so we're going to kind of back it up here. I'm going to go to my share screen here. So here's the lab. So just a quick recap. Here's the submit. It's the normal type of submit. Submit the lab write-up, submit photos, and submit answers to the assignment. And the background talks about acid-base reactions, talks about redox reactions, and it talks about gas-forming reactions. As far as the gas-forming reactions goes, it says basically look in your book. They're pretty straightforward. You want to wear goggles when you're working with acids and bases. Now, for materials, the three last materials are in your bag, along with hopefully three pipettes, three plastic pipettes. So the first reaction you're going to do is this redox reaction. And you want to find a penny minted after 83. And let me see if I can grab one. Okay, so the reason there's a penny shortage is because I have them all. Actually, I don't think there's a coin shortage anymore. So here's a penny minted after 1983. This one was minted in 2018. And you want to take this penny and you want to rub it on the concrete or a metal file. Okay, so I have some fingernail clippers here. And this has a little file on it. So what I'm going to do is I'm just going to file the edge of the penny on the fingernail clipper. Okay, that's good. Now, if I zoom in on the edge of this penny, which I'll be able to do once I find my remote. Okay, so there's the penny. All right, and if we look at the edge of the penny, you can see that it is coppery looking. And if I rotate the penny, you're going to see a spot right there where it's not coppery anymore. It's actually silver looking. Okay, so that is not a defect of the penny. It's where I actually filed the penny. So you can see Lincoln's head here. I'm going to take Lincoln's head and file the penny right above Lincoln's head.
So you're just trying to remove the copper plating?
Yeah, I'm taking the copper plating off. And if you take a look, here's Lincoln's head, right? And if you look right above Lincoln's head, you can see it's silvery now.
Yeah.
So you don't need to do this in a couple of spots, but you can if you want. And all you're going to do with that penny is you're going to get a cup of vinegar and you're going to throw the penny in there. And you're going to observe what happens where you have removed the copper from the edge of the penny. So hopefully we learned from the density lab that pennies are made out of zinc. They're not made out of copper. They're just copper coated. So what we're going to do is we're going to see why we copper coat the pennies, because something's going to happen with the zinc and the vinegar. And you know, if vinegar reacts with the zinc, then just about any weak acid will react with the zinc, even the acids in your fingers. And that pretty much explains why we coat zinc pennies and we don't leave them uncoated. Okay, do you kind of understand that first part?
Yeah.
And you want to write down your observations every half hour or so. And oops. For the acid-base neutralization reaction, you're going to take a red cabbage and you want to take a 3x3 leaf of red cabbage and blend it with a liter of water, or you could boil it in water. Either way, it'll work. Let me show you what you get when you do that. So I'm going to change my share. And I'm going to zoom out. And so I boiled it because I didn't want to clean out my blender. And this is what I get. Now, when I take a little bit of this solution and put it in this white cup, you can definitely see that it's colored. And here's a white cup that has nothing in it. And so this solution is definitely colored. Wouldn't you agree?
Yeah, it looks blue.
It should look blue. And I'm going to pour a little bit of water in this side just so that you know there's no optical illusion here. So here's just pure water. And if I shine the light down it, you can really see that there's no color there whatsoever. The shade makes it look like it's colored. Okay, so this cabbage juice is actually probably too dark. So I'm going to add some water to it.
Is this like for the pH test that you were mentioning before?
Yeah, this is the acid-base type reaction.
Okay, I have like pH paper laying around.
Oh, well, then you can use the pH paper. Well, what kind of pH paper is it?
I'll have to dig through my stuff.
If it's wide range, you can probably use it, but otherwise, I would just do this.
I mean, it seems pretty easy.
Well, this is
I was wondering,
really,
red cabbage.
what's that?
So I guess we'll see what happens.
Yeah, so let me show you kind of what happens here. So I'm going to make it a little darker. And you really want to have 4 cups. I only have 3. And you want to spread this out until you have even amounts in all your cups. Okay, so that's pretty even. And you can see all the cups, right?
Yeah, I can see all 3.
So what you want to do is you want to add 6 drops of sodium hydroxide solution to one of the cups. So I'm using 1 pipette for the sodium hydroxide, and I'm just going to add a drop in and swirl it. And it's hard for you to see, but I can see that that blue color has changed slightly from the other blue colors. And to me, it looks like it's more of a lighter blue, whereas the other ones look more like a steel blue or something like that. But can you see how that color is changing?
Yeah, it looks lighter to me too.
And it almost is turning a greenish color, maybe a green blue now.
Yeah, I see that.
And so we're going to add 6 drops of sodium hydroxide to that. And there we go. Now, one of the cups, you don't add anything to it, so you can compare it to the original color. So we'll make this middle cup the one that we don't add anything to it, so it stays the original color. And then you want to take your hydrochloric acid and do the same thing. Add it drop-wise and see what kind of color changes you see. So here's 1 drop. That's 3 drops. But you see how it's turning almost like a purplish color?
Yeah, I would say it's getting darker.
Yeah. And there's 4, 5, 6. And when I swirl it, I can really see the color in the bottom looks almost pinkish. Okay. Now I'm going to do something really quickly here, and I'm not going to add the hydrochloric acid or the sulfuric acid to the middle one. I'm just going to mix all 3 of these together, and I'm going to dump them. So I need to get a container to dump them into. All right, so I have an old pot here. I'm going to dump all the solutions out. And you saw how I diluted the solution, right? So now I'm going to try.
Oh, you diluted it with water before?
Yeah,
The cabbage, like the boiled cabbage water, how you diluted it first?
exactly. And I diluted it because sometimes if you don't have it dilute enough, you don't see a color change. And the reason you don't see a color change is because the indicator actually reacts with the acid in the base. And you can't really see that. All right, so here, let's see if working with the darker solution makes it easier to see what's going on, okay? All right. So here's my hydrochloric acid solution, and I'm going to add it in dropwise. And this is just an experiment to see whether or not making it diluted makes it easier to see what's going on. So there's 1 drop. There's 2 drops. There's 3, 4, 5, and 6. So can you tell that the solution has changed color?
Sorry, I was on mute. I can.
I can tell that it's changed color by looking at it. With the image, with the Elmo I have, it's kind of harder to tell.
I can see it. It's subtle, but I can see it.
And so we'll do the same with the sodium hydroxide. 1, 2, 3, 4, 5, 6. I'm just going to add 6 in. And yeah, we can see the color change. Okay. So you're going to add 6 drops of each to the solutions. And it looks like I don't really need to dilute the cabbage juice that I made. So I'm not going to dilute it anymore. And now the second part of the experiment is after you add the 6 drops and you watch the color change as you add the drops in, you're going to empty all 3 of these. So I'm going to empty the one with the hydrochloric acid in it. So the 2 on the end should look pretty much the same. And the one in the middle is a little greenish, okay? So what I'm going to do is I'm going to add 6 drops to this one of sodium hydroxide. Okay, so I have 6 drops of sodium hydroxide to these 2, and they should look pretty much the same color, don't you agree?
Yeah, pretty much.
Pretty much.
Mhm.
And these 2 look different, correct?
Yes.
So this one here that I'm leaving in the middle here is the original. Now what you're supposed to do is you're supposed to add to one of these ones where you added sodium hydroxide. You're supposed to add sulfuric acid drop by drop until it matches the one that we haven't added anything to. What we're trying to do is we're trying to neutralize the sodium hydroxide. So there's 1, 2, and I'm not going to count the drops. I'm just going to add until it seems to match the color on the right. And you see how it's getting pretty close?
Yeah, needs to be a little darker.
So it's almost there. And when you're doing this, you're actually supposed to be counting the drops. Okay, I think we're almost there. And I've gone too far. Because here, watch what happens when I add some more sulfuric acid. Can you see what happens? It turns pink.
Yeah.
So I knew I went too far because it started turning, instead of a blue, it started turning pink. So I blew that one. Let's see if so I would start that one over again. Now, here's the hydrochloric acid one. Where's my hydrochloric acid?
And pH paper, is it considered wide range if it's just 1 through 14?
Yeah, that's wide range.
Okay.
So what you would be doing is you would be adding, you wouldn't need the cabbage juice. You would just be putting the pH paper in after a drop to see what color the pH paper was.
Without it diluted?
Yeah. So what I'm doing now is I'm adding hydrochloric acid, hopefully trying to get the same color as the one on the right. And again, I think I went a little too far because now it looks kind of purplish when I look at it close up. So the idea there is to add it until it gets pretty much close to the same color. One of the problems I may have here is that I have more in this cup than I have in this cup, so it's kind of hard to match. When you use white cups like this, you want to use the same amount of each because the more solution you have in the cup, the darker the color. Does that make any sense?
Yeah, it'll be less opaque or more opaque if it has more.
So we want to make sure you use the same amount. So you're supposed to do that and observe the color changes. Okay, I'm going to dump that. So that's your acid base type of reaction stuff.
So with the cabbage, like how can you, does it get darker? Was the darker one the more basic one?
For the cabbage juice, the darker one was just the plain cabbage juice.
Oh, that's right.
And when you saw when I added a whole bunch of sulfuric acid to the solution, it turned it kind of pinkish, right?
Yeah.
So when you go from that bluish to a purplish or pinkish, it's an acid.
Okay.
For the base, it turned it kind of greenish. So when you add the base, it turns the cabbage juice kind of greenish. And you can play with.
Can you think that bases are kind of like cool colors and acids are warm colors?
I don't think that because it really depends on the indicator.
Right.
Different indicators turn different colors. There are some indicators that when you add base to them, they turn pink instead of bluish. And we're going to use an indicator like that when we do a vinegar titration. We're going to use something called phenolphthalein, and it turns pink when you get basic, not blue or green. So it really depends on the indicator that you're using. The cabbage juice actually has more than one indicator in there. So the different indicators work at different amounts of acidity. And that's why you can have more than two colors. With normal indicators, you only get two colors. So, maybe it's colorless and pink, or maybe it's blue and yellow, or maybe it's green and purple, or whatnot. You only get two colors normally. So with this cabbage juice, what's neat about it is you have all sorts of different colors that you can get. Now with your pH paper, you'll notice that if you look at the side of the container, it has a little legend for what color constitutes what pH, right?
Yeah, that's why I was wondering about the color.
So how is it that you can have so many colors in your pH paper? And the answer is your pH paper actually has the indicator dried onto it, and there's more than one indicator. So that's why there's
7 indicators if each one has usually 2.
Pardon me?
I'm confused. I guess it doesn't really matter how it works.
Well, if you look at it, there's probably 3 or 4 different indicators on your pH paper. And red cabbage juice probably has, 3 or 4 indicators in it. And at certain pHs, a certain indicator kind of takes over. Or indicators will react differently at a certain pH, and those colors blend together.
So do I just use the dropper like directly on the paper and then mix them together in a little?
No, I think what you want to do is you want to add a drop to the water. So you're not going to use cabbage juice. You're just going to use pure water, right?
Okay.
So what you want to do is you want to make sure you have the same amount of water in each cup.
Right.
And then to 1 cup, you want to add 1 drop of sodium hydroxide solution. And actually, before you put the sodium hydroxide solution in there, take your pH paper, stick it in the water, and see what pH it is. Okay.
Okay.
And you actually kind of want to report the color of your pH paper.
Report the color of the pH paper.
Yeah, report the color that you see plus the pH that it indicates on the container.
For just the water without anything.
Yeah, for just pure water.
Okay.
You should find out that the pH is really close to 7.
Right.
Okay. And then what you want to do is you want to add a drop of sodium hydroxide, and you want to take a fresh piece of pH paper, not a used one, but a fresh piece, and stick it in there. Now, does your pH paper come in strips or does it come in a long ribbon?
It's like a roll. It's a ribbon.
It's a ribbon. Okay, so what you can do is you can actually use like tweezers and cut a little, small little postage stamp off and stick that into the water and see.
Okay.
That way you don't stick a whole ribbon in there and waste it.
Yeah, it just needs like a little section.
Yeah. And even better would be this, is you cut them into little postage stamp size pieces, really small pieces. And when I say postage stamp, I mean square pieces, not really postage size. Are you with me?
Okay, because the ribbon's a lot thinner than
Right.
I mean,
And
it's
I don't want you to think I want you to make a stamp sized piece. You just need a tiny piece that is square.
okay.
And what would be better actually is for you to take your spatula. Do you remember the spatula from the previous experiment
Yeah,
for mixing?
the micro spatula.
Yeah. Dip it into the water and then touch one of those squares to see what color you get.
Oh, okay.
And the
Not
best thing to do is to have that little piece of paper on a piece of white paper so you can see the color really well.
Okay,
Does that make any sense?
it does.
And so on one white piece of paper, you might have 20 squares. So do the pure water and see what color you get. Add 1 drop of sodium hydroxide, stir it. Okay. And you don't want much water, maybe a centimeter worth of water in your cup. Add 1 drop of sodium hydroxide, stir it with your stir rod, and then touch a different piece of pH paper and see what color you get.
Okay.
And then do it a second time for 6 drops total. So by the time you're done with 6 drops, you will have recorded 7 colors. The color with no base in it, just pure water.
Right.
The color with 1 drop, 2 drops, all the way up to 6. Fair enough?
Right, for those 3?
Yeah. And then you would repeat it for HCl, and you'd repeat it for sulfuric acid. Only for HCl and sulfuric acid, you don't need to do pure water anymore because you already have that one.
Right.
Okay.
Okay.
So we're talking what? 6 times 3 is 18 plus 1. That's 19 pieces of 19 squares, if you will. Now I'm going to warn
me from going to the store.
What's that?
If it saves me from going to the store.
You might, but here's something I need to warn you about. If with 1 drop of sodium hydroxide, you don't really see a change, you need to not use the cups, but use even less water.
Right. So with the sodium hydroxide, I should see a change. Well, probably with all of these, I should see a change with 1 drop.
Well, hopefully. Well, let me show you something here real quick. I got to clean these out. You really don't want to spill the cabbage juice stuff because it'll make your house stink. So here, you can't see what I'm doing, but I'm going to change my share. And so part of this experiment is experimenting. Okay, can you see what's in the cup here?
Yeah.
And can you see what's in the cup here?
Yes.
Now I'm going to mix these 2 cups together so we know that they both have the same pH, right?
Okay.
Now I'm going to put just a little bit in this cup and the rest of it in this cup. And what I'm going to do here is I'm going to hopefully add some sulfuric acid to each of these, and let's see what happens, okay?
Okay.
Actually, I'm out of sulfuric acid, so I got to move on to sodium hydroxide since I have a lot of that. Okay, so this is the sodium hydroxide stuff. And I'm going to add 1 drop to each of these. I'm trying to get it so I can handle the bulb easily. There we go. So here's 1 drop to the one with less and 1 drop to the one with more. So if we take a look here, can you see how the one with less indicator in it, it's really easy to see that it turned kind of a pinkish.
Yeah.
And if I add 1 more drop here and 1 more drop here, you can see that this really isn't changing color anymore because 1 drop did it.
Right.
And
You really don't need much water.
yeah, and over here, it looks like it hasn't even changed yet. So probably that 1 centimeter of water is, in the cup is too much. It's
Okay.
probably just, cover the bottom so that you've got water in there.
Okay.
Okay. And maybe this one would be a little better if I actually had a little more. And you see how even with a little more, you can see the color change.
Yeah.
And I might be able to, my problem is that I am, I don't know which pipette I had in which container. So here, actually, I was adding acid to these. So here I'm going to add base to this one. 1 drop of base. And you see how it changed color?
Yeah.
So I would say this doesn't have quite a centimeter worth of solution in it, but that's about a centimeter. And here, if I add a drop of base, it kind of changes color. And if I add a drop of acid, it should change color, hopefully. Let's see. Yeah, that's hard to tell. Yeah, now it's starting to change color. So, in one of these cups that, you find at high school parties, if you put about a centimeter of liquid in it, it works out pretty well.
Okay.
So, the disposable cups that high school students buy so that they can drink when their parents are gone.
Mhm.
Or families use for picnics, depending on your particular background. You with me?
Yep.
And the red cups also work because the inside is white. So I just happen to have some of these ones that are white instead of red. I threw away all my red ones from my college days long ago. Okay, so do you understand kind of what you're doing there?
I do.
And with the pH paper, it's going to be a little tougher for you because you're going to have to stir with your stir rod and then touch the stir rod to the pH paper. Your stir rod or the spatula will be wet enough to actually wet the pH paper. Okay.
Okay.
All right.
I'll let you know. I might end up doing the cabbage. We'll see if it becomes too hard.
Well, the cabbage is kind of fun because
Sounds fun.
it's a pH indicator. I mean, that's about the only thing red cabbage is good for, unless you like coleslaw or stir fry. Oh, I need to change that to 0.1. For your gas forming reaction, this one's going to be really easy. Place a cup of vinegar in a large bowl or cup And when I say large, I mean like a 5-quart container. You with me?
Yeah.
Not just don't put a cup of vinegar in a large coffee cup, large bowl. I'm going to get rid of that cup. I'm going to put a large pot. Add food coloring and detergent if you wish. Now, the reason for that is that this is going to be a gas forming reaction. If you add detergent, bubbles will form and they'll fill up with gas.
Is the color just for fun?
Then color's just for fun.
Okay.
And then add a teaspoon of baking soda and record your observations. This is definitely one you want to do outside or in a sink, because if things go wrong,
Yeah.
it's an easy cleanup.
Especially with food coloring.
Yeah. So this is why the outside or in a sink. Don't do this on your kitchen table because it'll just be a mess to clean up. And this experiment, what you're actually doing is you're making that volcano. Have you ever seen that with science fairs?
Yep. I
Okay.
remember making one.
Yeah, so if you add red
Making
food
one
coloring,
too.
it makes it look like hot lava.
Right.
And you could actually, probably put stuff in the vinegar that does not dissolve, and that would probably well up, if you will. So you could probably throw some dirt in there and it would make it look more like lava. So you could have fun with it.
Maybe, yeah. Juice
So
some.
for the assignment, you're supposed to look in the book and find out what the definitions of are for acids and bases. There are Arrhenius acids and Bronsted acids, Arrhenius bases and Bronsted bases. And these aren't too hard to find. Let me do a share with you here so that we can look at my book. But before we do that, I need to dry off my tabletop. Okay, so I'm going to do a different share with you. So hopefully you can see my book now.
Yeah, I can.
Okay, so a lot of these things you can just look up in the index if you don't know where to find them in the chapter. And so if we look up Arrhenius, actually I'm closer to Bronsted Lowry, so Bronsted acid, it actually tells you what it is, proton donor. And a base is a proton acceptor. And you'll notice here that this is page 709, right?
Right.
But below that, we have 141. So what page do you think we want to go to since we're in chapter 3?
141.
Let's go to 141, shall we? So this is to make you guys do a little bit of reading here and try and figure out what these things are. So here you can see that this section is called the Arrhenius definition. And they show you how an acid behaves and a base behaves with the Arrhenius definition. And here we have the Bronsted-Lowry definition, and you can see they are writing out equations to show how they behave when they're Bronsted-Lowry acids and Bronsted-Lowry bases. So what I'm trying to get you to do is figure out, how do I write the reaction for an acid being an acid if it's an Arrhenius acid, and for an acid being an acid if it's a Bronsted-Lowry acid. Does that make any sense?
Yeah.
So I could just show it to you, but I want you to kind of read about that and see if you can figure that out. Because the ones I gave you are pretty similar to the ones in the book. I mean, if they're not dead on.
And the Bronsted-Lowry is pretty much the just donating the hydrogen plus or taking it.
Yeah, yeah. And we show that different ways in reactions. So Bronsted-Lowry is what we call a proton donor and proton acceptor. So it's all about the proton.
Okay.
And a Bronsted or an Arrhenius acid is something that makes protons in water. So the Bronsted-Lowry You don't need water.
So for the
Okay.
H plus, it's like an H plus with no electron?
That's what a proton is. Yeah. H plus with no electron.
Mhm.
And the reason for that is there are 3 hydrogen isotopes.
Right.
And let me see if I have some paper here. So I'm going to do a little writing here, which means I need to do my new share. Okay, so for hydrogen, there are 3 isotopes. There's H1, there's H2, and there's H3. And this guy looks like this, a single proton surrounded by an electron. This guy, which is the same size as this guy, has 1 electron, but it's got a proton and a neutron. And this, which is the same size as the other 2, has 1 electron, a proton, a neutron, and another neutron. So 99.985% are this one, 0.015% are this one, and 0% are this one. If we're looking at 100,000, we'd say 99,985 are this, 15 are this, and 0 are this. If you're looking at 100,000 of these, okay? I like whole numbers instead of decimals here. And this helps me to understand that, oh, none of them out of 100,000 will be this one. This guy is rare. Maybe you need 1,000,000 to get one. Does that make any sense?
Right.
And only 15 out of 100,000 are this one. Hydrogen atoms are H1s. Now, what happens if we take away the electron? It's a proton. So if this is H neutral, this is H plus, and that's why they call them protons.
Okay.
So areneous acids make protons in water. And even there's a couple of ways to do that. Okay, so I'm going to change the share back to the lab. So you want to define these things, write equations for HCl and NaOH behaving as an areneous acid and base respectively, HCl and NaOH behaving as a Bronsted-Lowry, I call it just Bronsted instead of Bronsted-Lowry, Bronsted acid and base respectively. And then I ask you to do it with water. Do it with water. And then finally, write a balanced neutralization reaction for aqueous HCl with aqueous NaOH. And then a balanced neutralization reaction for aqueous sulfuric acid with aqueous NaOH. And question 5 is, why should it take more drops of, actually, I need to change that. It should be less drops of H2SO4 to neutralize 6 drops of NaOH. So remember that experiment where we're adding H2SO4 and HCl to the NaOH solutions until we get the same color?
Right.
Should take fewer drops of H2SO4. Now, I'm going to change this now before I forget. So I need to go to my edit screen. I might be in the edit. Let's see. Why should it take fewer? I am in my edit screen. So the reason I have you do number 4 is because it's supposed to help you with number 5.
Okay.
Now, number 6, it's a redox reaction. You're supposed to write a balanced reaction. And you're supposed to assign oxidation numbers to each atom. I'll probably be talking about that tomorrow when we do problems. Using oxidation numbers to determine what was oxidized, oiled, lost electrons, and is the reducing agent. These terms become more understandable when you listen to the redox lecture.
Okay.
And for the gas forming reaction, you write a balanced reaction, and this one's very straightforward also. Now, for the down here, you're supposed to figure out what types of reactions these are. And I have too many arrows, so I need to get rid of some of those. So let's see here.
So you're just supposed to tell if they're an acid base, precipitate, blah, blah, blah.
Pardon me?
You're just supposed to tell if it's an acid base reaction or a precipitate reaction or redox.
Yeah, you're supposed to tell me what kind it is, but also you're supposed to show me what you make
Oh, okay.
and balance the reaction. So you see, if you take a look below our examples of a precipitation reaction, acid-base reaction, a redox reaction, and a gas-forming reaction, each needing to be completed.
Mm.
So just because I say it's an acid-base in this order doesn't mean, like, this first one isn't necessarily a precipitation reaction. You with me there?
Right.
And the second one isn't necessarily a redox reaction. You have to figure out which one is which and complete them. And then 9 says, briefly describe how you can determine how to classify each reaction. Like, how do you know this one is this? How do you know this one is that?
Just a quick answer. How do you determine?
Well, how would you know it's an acid-base reaction? You should have an acid and a base.
Right.
So how are formulas of acids written? They're usually written with hydrogen at the front. Okay. So are there any acids in this one here? First one?
Hydrochloric.
Yep. How about the second one?
There's a base.
That's the question is, are there any acids?
No.
Okay. How about the third one?
No.
How about the fourth one?
Yes.
Yeah. Okay. So either the first or the last one is an acid-base reaction, right?
Right.
And now you want a base. So what are common bases? Well, normally bases have this OH in it.
Right.
And here you have this HCO3. So, well, probably the last one's an acid base.
Right.
So that's 1 out of 3. Or 1 out of 4 that we're done with. You'll find that redox reactions normally have a pure element in there somewhere.
Okay. So it's usually.
So which one is your redox?
The third one.
Right. And so now you have a precipitation reaction versus a gas forming reaction. I'm going to give you a hint. Whenever you see CO3 with an acid, you're going to make CO2.
Okay.
So that's your gas forming. So what's the last one, the middle or second one have to be?
The second one is a precipitate.
Right. So those are the kind of things that I look for. First, I look, is there an obvious acid and base? That's an acid-base reaction. Boom.
Okay.
Is there a pure element in the reaction somewhere? Redox. And then, is there carbonate in it? If there's carbonate in it and an acid, I think gas forming. And then usually precipitation is the one I leave for last. It's kind of like a process of elimination.
Right.
Now, also for precipitation reactions, you expect to see 2 aqueous things reacting and both of them to be ionic.
Right. And then it forms the solid and the aqueous.
So look at the first reaction. Are they both aqueous?
Yes.
Are they both ionic? The answer is no. HCl is not an ionic compound. Okay.
Not sure. So
how about the third one? Are they ionic?
No.
Are they aqueous? Nope. How about the fourth one? Are they aqueous?
Yes.
Are they both ionic?
Yeah.
No. Remember, ionic is metal and non-metal, right?
Okay. I got confused with where boron was.
Boron's a metalloid. So normally in formulas, we treat it as a non-metal.
Okay.
Metalloids behave more like non-metals when it comes to bonding.
Right. It has to be a metal.
You have a molecular compound and you have a ionic compound. It's probably not going to be precipitation.
Okay.
So, my precipitation is kind of like, okay, that's the last one I get to, but I still want to see two ionic compounds reacting and two aqueous ionic compounds. So, that's how I would describe it. I'd go, well, if it's an acid base, I look for formulas that look like acids or bases, right?
Right.
And you want a little more detail, like the acid begins with H, the base usually has OH, and is ionic. So that's the kind of stuff you do.
And we should, the pretty much the states of each one for each reaction will always be the same.
Pretty much. I did not give you the states for the third one, but I could. For instance, the state on this guy is a gas. And the state on this guy, what's the state of O2?
Gas.
Gas. Okay. So that third one we already said is a redox reaction, but it's a special type of redox reaction we call combustion.
Right.
And so you want to classify it and complete it. And combustion reactions have particular products.
So tomorrow you were mentioning we're gonna go over maybe redox.
Let me take a look at the problems, and I can tell you exactly where we're going to be headed tomorrow. So we're at like problem 28.
Okay.
So if we look at 28, you can see it's a precipitation problem. 30 is about, oh, you can't see that. Okay, so if we look at 28, you can see it's a precipitation problem.
Right.
30 is a ionization of perchloric acid and water. That sounds like an acid base thing.
Right.
More acid base.
So the more
Balance.
hydrogens in an
Pardon me?
acid, the more hydrogens in an acid, usually the weaker it'll be.
No,
Just
the
kind
number
of.
of hydrogens does not really tell you whether it's weak or strong.
So you just have to memorize those.
Yeah.
Okay.
And it's just easier to memorize the strong ones because the other ones are probably weak.
Right.
So more acid base, more acid base. We'll skip that one. More acid base, more acid base. And here, this is going to be probably, this is probably going to be a precipitation. And this one is going to be an acid base, gas forming. And then here, when we get to number 54, we start talking about redox.
Okay.
So to help you understand redox reactions, you want to be able to assign redox numbers. And we have rules for that. And the rules are pretty simple, but they're hard to apply. For instance, like every atom gets an oxidation number. So how many oxidation numbers are we going to have here?
I mean, 7.
7, right. Now, it turns out that when you have things like this, the oxidation number of the fluorines all end up being the same. So even though we're going to have 7 oxidation numbers, 6 will be identical and 1 will be different. Does that make any sense?
Yeah.
So here we have 7 oxidation numbers, but how many different ones?
Well, 5 of them will be different from the other 2.
And 2 will be the same. So 2 different ones.
Right.
And we have certain rules for assigning oxidation numbers, like an oxidation number in a pure element is 0. So if you have pure oxygen, what are the oxidation numbers? 0. If you have pure sodium, what are the oxidation number? 0. So anything that's pure.
It doesn't oxidize?
What's that?
What does that mean if the oxidation number is 0?
It just means that it doesn't really mean anything. It just means that we can use it to find out in a reaction if something is oxidized or reduced.
Oh, okay.
That's
I
all.
barely remember this stuff from high school, so
So redox, just quickly, is an exchange, not an exchange. It's a movement of electrons. And the way I like to remember it is oil rig. Oil is oxidation, and rig is reduction. And so that's why it's called redox, read or red ox. Now, the oil means loss of electrons. That's what the L stands for. The G means gain of electrons. And if you're getting oxidized, you're the reducing agent. And if you're getting reduced, you're the oxidizing agent. And there are other things. There's one more thing you can get from all of this. And well, let me show you real quick. If you take carbon and react it with oxygen, you get CO2. Now, what did I tell you about the oxidation number of pure elements?
0.
Okay, so this is a 0 and this is a 0. And since there's 2 atoms here, it's 0 each. So one of the rules for oxidation numbers are that if it's a pure element, it's 0. If it's a monatomic ion, it's equal to the charge. So do we have any ions here?
No.
No, we don't. So we can't use this one. And then if it's not in a monatomic ion, but it's a compound or polyatomic ion, normally when you assign oxidation numbers, you do it in this order. Fluorine is -1. Oxygen is -2. Well, I should say hydrogen is +1. Oxygen is -2. Chlorine is -1. But you do these in order. And then there's another rule that says the sum of the oxidation numbers has to equal the charge on the compound or ion. So here, for this guy, you can't use this. You can't use monatomic ion. You can't use F as -1. You can't use H as +1, but you can use O as -2, right?
Right.
So that's -2 each. So that means we're looking at a -2 and a -2 and whatever carbon happens to be. Now, what's the charge on this compound? CO2.
-4 plus 4 minus.
Well, that's if it's made out of ions. Is it made out of ions?
No. So
No. So what's the charge on it?
does it not have a charge?
It does not have a charge.
Okay.
So all of these have to equal 0. What's the oxidation number of carbon?
That makes sense. Well, we already had it at 0.
This one is at 0, but I'm talking about here. What's the oxidation number?
2 plus?
How about 4?
Oh yeah, 4, because it's 2 and 2.
Because it has to add up to 0. So here's how you use oxidation numbers. So you asked, what are oxidations used for? Oxidation numbers. Do you see how the oxidation number goes up for carbon?
Right.
And you see how it goes down for oxygen?
Right. So oxygen's the reduced one?
Yeah, oxygen got reduced. And if it's reduced, did it lose electrons or gain electrons?
gained electrons.
Gain electrons. What type of agent is it?
The oxidizing agent.
What? Oxygen's an oxidizing agent? Oh my God.
Okay.
So when oxygen gets oxidized, or when oxygen gets reduced, it oxidizes something else. And so here, arrow up means oxidized or oxidation, same thing. And O means oil. Oil means loss of electrons because of the L, and it's the reducing agent. So that's what you use oxidation numbers for, is to figure out what happened.
Okay.
And so it turns out these oxygens are actually getting electrons. And it's hard to see when you look at this. You're like, well, where are they coming from and where are they going?
Is this another one that can like go both ways too?
No, this is a very, you mean a reversible reaction?
Yeah, like the ones that are like at equilibrium, you'll always have two arrows.
Yeah. Well, no, this is not really considered to be a reversible reaction. In fact, there aren't many things that can take CO2 and use it.
Right.
Well, I mean, there are lots of things that can do it, but none of them are animals. What kind of organisms use CO2?
Plants.
Plants. So yeah, plants can kind of do this, but they don't make this. They actually make sugar.
Right.
So that even this doesn't happen. So yeah, this is not considered to be reversible. If you take carbon and react it with oxygen to make it CO2, that's the end of the game.
Okay.
Okay.
Yep.
Most of our reversible reactions are going to be with weak acids. Okay.
Right.
So that's your lab. Kind of have a little bit of fun with it. You're going to have to experiment to see, if you can see a color change. And if you can't see a color change, you're probably using too much solution. And since you have a limited amount of your base and your acids, you want to make sure that if you're not seeing a color change, that you make adjustments before you use all that stuff up. Okay.
Right. Okay, sounds good.
All right, Rebecca. We'll catch you later. So hopefully
All right.
tomorrow.
Have a good day.
You too.